Good morning, good afternoon, and good evening. Welcoming everyone who is joining us for the SNIA Networking Storage Forum sponsored presentation today. The presentation will be covering where does SPDK fit in the NVMe over fabric landscape. With me today are two industry experts that will be presenting for you, and I'll be your moderator. Before I introduce your speakers, I'd like to quickly cover a few BrightTalk interface things. First, some of the slides and text may be slightly small, so I'd recommend enlarging your viewing area to full screen. Also, on the right-hand side, you'll find a chat box where you can ask questions from your presenters. We encourage you to ask the questions and to make this presentation interactive. Oftentimes, we have such great responses on the questions that it's hard to cover them in the allotted time. If that does occur here, we will be releasing a blog to the SNIA website after the webinar that will contain all the questions. As well, if you look, there is an attachment and links section just underneath the questions. Right there you will find the presentation today in a PDF format, as well as a couple other links, some of them that will be the performance data, which Ben will cover within the presentation. Finally, we do request that at the end of the presentation, you rate this. The rating is between 1 and 5 stars, with 5 being the best. There's also a section for comments and suggestions. We'd love to hear from you. We value your comments as they do help us improve the quality of these presentations. So real quick, introducing our presenters. My name is Tim Lustig. I represent Mellanox at SNIA in a marketing role, and I'll be your moderator today. And with me today is Jim Harris and Ben Walker from Intel. Jim is a principal software engineer in Intel's data center group and a core maintainer of the Storage Performance Developers Kit. Jim started on the SPDK project at Intel in 2013 to demonstrate how to build performant and efficient storage software for non-volatile media based on the NVMe Express protocol. Jim has served in a wide variety of storage software-related roles during his 18 years at Intel. He holds a BS and MS in computer science from Case Western Reserve University. Also with us today is Ben Walker, who is a core maintainer of the Storage Performance Development Kit, a toolkit that contains building blocks for developing storage applications in user space. He has worked extensively on the user space NVMe driver, the block layer, a persistent block allocator, and is a primary contributor to the NVMe over Fabrics target. Ben has worked in storage at Intel for 9 years in a range of roles, including most notably technical lead of Intel's Rapid Store technology. Prior to working in the software storage, Ben worked on a high-energy physics simulation and data processing. He has a BS in physics from Arizona State University. Real quick before we jump into this presentation, I want to cover a few things about our sponsor, SNIA. We are a global industry association chartered with advancing the adoption of storage. Within our charter, it is to remain vendor neutral, and we have representations from over 185 different industries, as well as over 2,000 active contributing members. As a global organization, we reach over 50,000 end users worldwide and focus on standard adoption and education. Finally, this slide right here, just cover it real quick. SNIA's membership is a community participation in the following storage and related technical working groups. So there's quite a diverse area of coverage that we have here at SNIA. Feel free to visit the website, and you can sign up to attend other groups, or read our blogs, and view educational information there as well. One last thing before we jump into this presentation, this of course is the legal notice our lawyers make us include. Shouldn't surprise anybody, it's just standard legal talk. The material that you'll be seeing today is copyrighted by SNIA, and any use of the material within the presentation is permitted as long as the slide is reproduced in its entirety and SNIA is referenced to the source. And be aware that that we make no warranties, expressions, or implied information that is presented. You'll be using this at your own risk. And with that all said and behind us, just a real quick want to introduce the agenda today. We'll be going over the SPDK project. This is where Jim will take over. He will be covering the key use cases for NVMe with SPDK. And then he'll go ahead and turn it over to Ben, who will be covering the architecture and design and performance data. At the very end, we'll wrap up with Q&A. If we do have some time during the presentation as well, in between slide breaks and transitions, we will have an opportunity to answer some of the questions. As long as we stay on schedule, we'll go ahead and move that way. If we are falling behind a little bit, we will save all the questions to the end. Without any further ado, I'd like to introduce Jim to take over the first part of the presentation.
Hey, thank you, Tim. Looking forward to doing this presentation today. So a little bit of a background here. I was talking with Jay Metz from Cisco a couple months ago. He had attended some of the SPDK talks at SDC in San Jose last summer, and he had said that he thought the talks were really good. SPDK has been around a long time. We're not really doing overview type presentations at those conferences, and he thought kind of stepping back and giving an overview of the project, and especially in the context of NVMe over Fabrics, might be really helpful. So I'm hoping that you'll get a lot out of this presentation today. So starting with a little bit of an overview. So SPDK is an open source project. We call it an open source project. I would say it's more of an open source community. So this isn't a case where it's just some source code that's out on GitHub. We have an active mailing list, Slack channels. We have semi-annual summits. In fact, we'll be having another one in the Bay Area this April. Do all of our public code reviews on Garrett Hub, etc. So we really intend for this to be not just a project where code is getting put out online, but where people can come and ask questions and contribute and really make it a community. As you heard in the intros for Ben and myself, we really intended SPDK to be a framework for highly performant and efficient storage software. When the project first started, this was before NVMe SSDs were really available at all, but we saw as what the performance was going to yield was that the status quo when it came to storage software wasn't going to suffice to unleash the NVMe performance. We had seen some of this with packet processing and 10 gig Ethernet maybe 10 to 15 years ago, and now we were going to see some of those same challenges on the storage software side. So the goal here was really to be able to do millions of IOPS on a system or even on a CPU core, which meant that we really needed to eliminate interrupts, context switching, system calls, and going to a user space pulled mode programming model was what was going to be needed to enable that level of performance. We're seeing that a lot of these concepts can apply to the kernel as well. In fact, last year the Linux kernel added a I/O facility called IOU ring, which has adopted some of the principles of SPDK and is enabling the kernel to get higher performance and efficiency as well. But we still see SPDK still has the advantage when it comes to really maximizing the efficiency of storage software. So SPDK has a broad range of storage protocols and features. I'm going to talk about those more in the next couple of slides, but from the beginning, NVMe Express was the focus. When this first started, that was really why we started this project, and I'd say that's especially even more now with NVMe over Fabrics. And so there's a lot of components to SPDK, but really everything we do for NVMe Express is really the underpinnings of this project. And I've talked about storage networking from an NVMe over Fabrics perspective. We have support for iSCSI, but this also supports storage virtualization use cases through something called vhost. We're not going to go into details on that today. You can check out the blog links in the attachments here to get an access to our blog, and there's some links there for storage virtualization with SPDK if that's something that you're more interested in. And then finally here, there's two primary, advanced too far. There's two primary ways SPDK can be deployed. So SPDK is a set of libraries. So for example, we have one library that's just the SPDK NVMe driver. I'm going to go into some more details on what some of those are. But one use case is basically just taking one or two of those libraries and integrating them into an existing storage application. But then SPDK also provides fully functional applications. So for example, we have a fully functional NVMe over Fabrics target that provides block storage with an NVMe SSD backend and a JSON RPC interface for doing configuration. So depending on your use case, some people may want to start with one of those applications and make modifications. Other people may want to just integrate the components that make sense for their use case. Okay, so next, a little bit of the project history here. So this project started in 2013. Let's see here. As an internal project within Intel. We had a pretty cool code name called Waikiki Beach. We started this, there was a collaboration. Our team was aligned closely within Intel with the packet processing group that was doing DPDK, the data plane development kit. And we were looking at how can we take some of those concepts that they've been using for packet processing and apply not just the concepts, but also some of that code to storage. And so then also at the time I was working on FreeBSD and had recently submitted the NVMe support for FreeBSD into the upstream, their upstream kernel. And so we had a nice alignment here from both a technical perspective and then also a licensing perspective with FreeBSD being BSD licensed to start this Waikiki Beach project. NVMe over Fabrics wasn't in the picture yet, so we started with a BSD licensed iSCSI target called ISTGT, and that was the basis for the original Waikiki Beach to do iSCSI with an NVM Express backend. There's been a lot of modifications made to both of those over the last 6 years, but you can still see some of the remnants of that original integration. So it was pretty apparent within the first year or so that the restricted license that Intel had on Waikiki Beach at the beginning wasn't going to work to get SPDK or Waikiki Beach at the time to be more broadly adopted by the industry. And so fairly quickly we moved towards a permissive BSD license. This is also when we got rid of the fun name Waikiki Beach and went to a more traditional Intel acronym SPDK. We released that NVMe driver out on GitHub. At first, it was just the NVMe driver, but within a year, we had all of SPDK out on GitHub through a BSD license. And that's the model that's continued to this day, where all of the active work that's happening in SPDK is done out there on GitHub. Pretty quickly after that was out on GitHub, we started getting pull requests. So that was really exciting. We were seeing people outside of Intel using SPDK, not just using it, but also wanting to contribute. And shortly after that, we started having some SPDK summits. We had one in Shanghai in 2016. We started having ones in the US in 2017. Shortly after that, we had a small developer summit, which we still do on a yearly basis, where instead of presentations like you might see at SDC, it's more getting a bunch of developers into a room and kind of like a hackathon, hashing out development architecture ideas. And at this point, we had Shuhei Matsumoto from Hitachi had come into Chandler, Arizona for this summit. He had been extremely active in the community, doing a lot of contributions, especially around iSCSI. And he was the first core maintainer that we had from outside of Intel. And so we've really been trying to adopt this model. Actually, just last month, we also added a developer from Mellanox, Alexei Marchuk, as another core maintainer. And these core maintainers are really the ones that kind of help drive the project forward. They're really responsible for deciding if and when patches get merged, and just really kind of balancing, helping the SPDK project move forward while still contributing to meet those maintainers or company specific goals. So around that same time, NVMe over Fabrics and the RDMA transport had been, the specification for that had been released. SPDK had support for that out. But what we were seeing is a TCP specification was being developed that we started getting a lot of questions about when SPDK was going to have support for that. We had been working on this internally. We weren't able to make it broadly available because the specification hadn't been released yet. But we did start providing those patches to NVMe member companies prior to the spec release. And so then once the the TCP spec was released in late 2018, we had all the SPDK support for TCP on both the initiator and the target side was all completed in line with the spec, and it was part of the NVMe announcement. And finally, we continue to see the community growing. The Slack channels, the mailing lists, GitHub are always extremely active with discussions. As I mentioned, we just announced our 4th annual summit in the Bay Area this coming April. And this last year, we had over 700 patches come in from over 50 contributors, and that's just from people outside of Intel. So this really is an open source community. There's a ton of contributions that are coming in across the industry. Okay, so a little bit on the architecture diagram of SPDK. I talked a little bit about how this is really a set of building blocks. So yeah, we do have full, full applications, a full NVMe-over Fabrics target application that you can start on a system and be able to drive I/O to it. But underneath, there's a whole bunch of different libraries, and I'm just going to talk through some of those main pieces here for the next couple minutes. So at the bottom, we have our drivers. So this is typically our NVMe host driver, which originally supported just PCIe. More recently, it's added support for RDMA and TCP. And so you have a common NVMe interface that can be used to interact with either local or remote NVMe controllers. This is very similar to what the Linux kernel does as far as having a lot of core functionality and then plugins for the individual transports. And then we also have pulled mode drivers for VirtIO if you're doing this type of SPDK user space pulled mode programming within a virtual machine. Next, we have we call our block storage providers. So SPDK has a generic block interface called the BDEV layer, very similar to what you see in the Linux kernel block layer. We have a number of modules that can provide block storage to upper layers of the application. So NVMe is the main one, but we also have ones for things like Linux AIO and IOU ring. If you have storage that's being presented by the Linux kernel, but you want to present that through some of the SPDK, upper layer transports. We have other ones for things like VirtIO, iSCSI initiator, CephRBD. But this is all stackable. So we have a number of block storage services as well that, again, all work within this BDEV layer to do things like partitioning. We have a native SPDK logical volume implementation built on the block allocator that was mentioned during Ben's intro. We have support for things like transforms like crypto and compression, where you can use either optimized software libraries like ISA-L, or you can offload the crypto and compression algorithms to accelerators such as Intel Quick Assist. There's support in upstream SPDK for doing caching through the OpenCAS framework. And there's also some basic RAID 0 striping functionality as well. And then at the top, we have the storage networking and storage virtualization. Ben's going to talk more about NVMe over Fabrics, so I'm not going to cover that. But we do have vhost support where you can either present virtualized SCSI controllers or just raw block devices to a VM. We also have some basic file system support, something we call blobfs. This is really intended for log structured merge tree implementations like what you would see with RocksDB. So it provides the ability for SPDK to provide storage into an application or a library like RocksDB that requires file semantics rather than block. And then we have our integration points. We've added support into upstream Cinder for being able to provision SPDK-based storage with a Cinder plugin. I mentioned a little bit about the RocksDB integration. There's also ongoing work within the Ceph community with their OSD redesign to be able to use SPDK to access storage most efficiently. And then we have a number of tools. FIO We have SPDK plugins for people who are familiar with FIO, have scripts that already work with FIO, that you can use FIO with the SPDK drivers. We also provide custom benchmarking tools for SPDK. We've actually found that in very high performance, stressful use cases that FIO has just enough overhead that it actually restricts the performance. So depending on the use case, those are both available. And then we have support for other things like NVMe CLI, and we have a custom SPDK CLI tool for doing configuration. Okay, so going over some of the key use cases. So for determining factors, for deciding is SPDK right for your use case, obviously performance and efficiency is a big one. SPDK is capable of up to millions of IOPS per core. Another determining factor is integration with existing software. So if you're building something from the ground up, SPDK may work very well. If you already have existing software, depending on how that's already designed and architected, there might be some considerations there. On the customization side, SPDK enables use of optional or vendor-specific NVMe features, and there's really no performance impact. So it's very easy, when you talk about things like zone namespaces or some of the work that's being done in NVMe around key value, these SPDK interfaces work just as well with those types of APIs as they do with traditional block storage. And then licensing. Sometimes licensing is concerned. SPDK is BSD licensed. It's permissively, so it's very permissive. Of course, SPDK welcomes contributions back to the community, but it does make it easier for companies who may have some IP concerns where SPDK might be a good option. So the primary use cases here, obviously the NVMe-over-Fabrics target library itself is really the big one. Ben's going to go into more details on that, but this is a library that can be integrated into an application in a few different ways. One is to take some of the existing SPDK blocks for doing things like accessing an SSD, doing logical volumes where you can logically partition it, and then present different logical volumes to different clients over the network. Another key one is where possibly you already have an existing storage stack that does block storage, but you want to add NVMe support to it. So this is where you can basically build a custom block device module that has your custom logic in it, and it just bolts right under that NVMe over Fabrics target, and you can use that SPDK target software as is. And next, there's support here to basically build what we would call custom transports. So obviously, over a network fabric is the primary use case, but we're seeing cases with like SmartNICs where you can use this NVMe over Fabrics target library as the front end to, or I guess the back end of the SmartNIC to take commands from the host and be able to process on a SmartNIC. We're also doing some work with Nutanix around adding what we call a mediated user transport. So basically for virtualization, being able to present an NVMe virtual SSD to a virtual machine, and then be able to process the back end using the NVMe over Fabrics target. And so then for those use cases, it shows where some of the NVMe support we have on the driver side for Fabrics works well. So you can imagine if you have a SmartNIC, you're using the NVMe over Fabrics target to take commands from the host, but then you want to forward them over a network fabric, you can use the SPDK NVMe driver to be able to do that. So some of the cases where SPDK may not be suited, obviously if you have an environment or an application where maybe the performance requirements aren't excessive, maybe it's just tens of thousands of IOPS, using the kernel-based storage software is probably going to be sufficient for your needs. Moving to something like SPDK, where there is a little bit of a barrier to entry, may not make sense in that use case. Integration with legacy software. So all of the SPDK APIs are designed for asynchronous operation with a relatively fixed number of threads. And so depending on the software that's being integrated, if it's built more on POSIX type semantics with lots of threads doing more blocking, there might be a little bit more work to be able to integrate with SPDK in that case. It can be done, but it's just a little bit more work that needs to be done. Support requirements, kernel-based solutions may provide some support options that aren't available with SPDK today. The community is very responsive as far as taking bug reports, doing regular releases, but it's not going to be as much as maybe what you might be able to get with a contract with with an ISV that can provide support on the Linux kernel. And then finally, for cases where there's some general purpose file system requirements, things like NFS, SPDK is not really a good fit there yet. Today, we do provide some of the very basic file storage services with blobfs for some of those, things like log structured merge trees, where you just have a unlimited number of files and a flat directory structure. SPDK fits really well right there, but for more general purpose file system, that's typically best, still done within the Linux kernel. Okay. So with that, I'm going to hand this over to Ben. Ben is really the expert on SPDK and NVMe over Fabrics, and he's going to go into more details on the architecture and design.
All right, so we're going to go through a high-level overview of the parts of this NVMe over Fabric target. Specifically, we'll cover the host a little bit toward the end, and then we'll end on some performance data. So I'll start with a overall picture of the target, and maybe the best place to start is defining what I mean by target. That's the server in NVMe over Fabrics. I don't actually believe the word target appears in the specification, but it is the traditional name for it, taken from iSCSI primarily. So when I say target, I mean the server side. The other term I'm going to use is host, and that is in the NVMe over Fabric specification, and that means the client, which I know for networking people is the exact opposite meaning of what you would expect. But this is coming from people who are building PCIe devices and plugging them into a host system, right? So the host is the client. Okay, so what we'll do from here is dive into the individual pieces of this picture, because obviously this picture is very, very complex. So we'll start by talking about some of the highest level primitives inside the software. By primitives, I mean the software building blocks, the things you interact with in the code. They're basically represented by structs. SPDK is all written in C. They're the things you operate on and put together. So the first two I'd like to cover are transports and subsystems. And so in SPDK, there are currently 3 transports. There also are 3 defined in the specification. But it is a generic plugin system, and we can add more. As Jim had outlined, there's currently a patch out to add another that is still very much a work in progress, which is a virtualization transport, much like VirtIO block or VirtIO SCSI, but it presents what appears to be a real NVMe device into the guest VM, and the guest VM can run the regular NVMe driver in its operating system against it. And it's backed by the NVMe over Fabrics target in SPDK. I'll go into a little bit more about some of the other interesting aspects of these transports in a later slide. The only other note here is that the TCP transport is actually based on top of another pluggable abstraction for sockets. So we have a socket abstraction layer that abstracts socket operations that has a plugin system as well, and so the TCP layer uses that. The default implementation is basic POSIX sockets, connect, read, write, etc. But we do have lots of other implementations of that socket layer, either in the works or already available, ranging from user space ones like VVP to alternate methods of interacting with sockets through the Linux kernel like IOU ring. or there's work from Mellanox on their user space stack called VMA. There's a lot of active work in changing the way SPDK specifically interacts with the network right now. That's one of the most active areas of development. All right. So the other major type of thing inside of a target is subsystems, which we can go into now. Slide transition. Okay. So an NVMe-over-Fabrics subsystem is a concept right out of the specification. In SPDK, they are globally visible, and I'll explain what I mean by that. In NVMe-over-Fabrics, subsystems contain controllers and I'll call them namespace entries. Basically, they have an array of valid namespace IDs that point at a real namespace. And so a namespace is a set of logical blocks indexed from 0 to n. In NVMe-over-Fabrics, a controller is just a network session, and these are actually transient things, very unlike a physical NVMe device where the controller is like an actual chip soldered onto the board. These are transient things that are established whenever a new host client connects. But they sort of present themselves as if they were physical controllers, and they emulate all the register state that a physical controller would have. So subsystems in NVMe-over-Fabrics are effectively access control lists. They are not physical things. They're just mapping which clients are connected to which backing storage devices. And they may enforce rules on who can connect where. And so the controller structure is globally visible in SPDK, and by that I mean any thread in SPDK can read data out of the subsystem. They're typically read-only. They have a state machine in them, and so when the whole subsystem is active, they're read-only. Any thread can look at the data in them and know that it's thread-safe. In order to modify a subsystem, the state machine has to transition to pause, which involves sending a message to all of the other threads and informing them that this subsystem is paused. And then when you get all through that process, you can then make the change and resume them. And the reason it's so complex, we could just take a lock, right? But the reason we do it this way is because SPDK is about performance at all costs, right? So the cost of not taking a lock in the I/O path to check the subsystem, the subsystem state has changed, is that you have to do this more complex messaging setup when you do need to change it. But that's key to our performance. All right. Okay, and then there's another set of top-level things in the NVMe-over-Fabrics target that were on the first slide that are called pull groups. And so a pull group is just, in the most general sense, a collection of things that can be pulled as a unit. And unlike the other two top-level primitives I just showed, pull groups have a per-thread scope, which means they are only accessible from a single thread at a time. And so they also don't need locks because only one thread is accessing them. In general, you can think of most of the software designs in SPDK as elaborate schemes to avoid cross-thread locking and coordination. And so this pattern of having globally visible read-only objects and then per thread, effectively caches of data related to that object is a very common pattern. It happens all the time in SPDK all over. And it actually even happens in NVMe, where you have sort of the controller, which is more or less a static thing, and then you have queue pairs, which every thread can have their own and operate on those, and they have state they keep specific to the queue pair, like the SQ head and things. And so you'll see here that these pull groups have things inside of them that mirror those two global types of primitives. There's transport pull groups, which there's one of those per transport, and there's subsystem pull groups, and there's one of those per subsystem, and this is all in a pull group, so per thread. All right. So if we dive into what those two things are, a transport pull group is effectively a collection of connections that can be pulled efficiently as a unit. Usually transports have some mechanism to pull a set of connections more efficiently than pulling an individual connection. And SPDK is all pulled mode. And so if we put a concrete example on this, in the TCP transport by spec, an NVMe over Fabrics queue pair is a connection. It's basically a socket. And there is an efficient mechanism, more efficient mechanism, to pull a set of sockets in Linux called ePull, and there's one on FreeBSD called KQ. And so the transport pull group is basically an ePull file descriptor that we've added a bunch of sockets to. And so when you pull the pull group, it just does an ePull wait, non-blocking ePull wait, to ask if any of the sockets in the set have data to receive. Beyond being grouped in a way that makes them efficient to pull together, the queue pairs, or these connections, are not actually otherwise related to one another. So they're not all from the same controller. They're not all from the same, targeting the same SSD in the back end. They're just an arbitrary grouping of connections that we can pull as a unit. And so all of the network transports we have so far do have some more efficient way to pull sets, like RDMA has shared completion queues and Fiber Channel has hardware queue pairs. Oh, I think I went 2 slides. We'll go back. Okay, and so then the other primitive inside of the top-level pull group was the subsystem pull group. And in SPDK, namespaces that are presented through subsystems are SPDK BDEVs. And so Jim talked a bit about the SPDK BDEV layer. Any BDEV, whether it's a logical volume or it's an actual NVMe device or whatever, can be presented as a namespace into through a subsystem in NVMe over Fabrics. And so the global subsystem structure has effectively an array where the index is the namespace ID and the value is a pointer to an SPDK BDEV. And inside of the subsystem pull groups, we have this pattern again in the BDEV layer where you have the global BDEV object, and then every thread needs a per-thread I/O channel associated with that BDEV in order to submit I/O operations. Just like in NVMe, you have a global controller, and every thread has its own queue pair that it can submit I/O on. And so inside these subsystem pull groups is another array, again indexed by namespace ID, but the value is the I/O channel for that BDEV to be used on this particular thread. All right. So from here, I'm going to go through 2 flows just to sort of outline probably the 2 most important operations that we have in the target. The first one is accepting a connection. The second one will be the I/O path. And then we'll get into the performance data. So to accept a new connection, at the beginning of time for this target, the administrator sets up a set of addresses on which it should be listening. This is an actual call to listen for the socket layer. There's equivalent things in RDMA and Fiber Channel. And so the target is listening globally. And then it configures which subsystems are allowed to accept new connections from that listen address. Because again, the subsystem is an access control list, so it's configured per subsystem. It says, this subsystem can accept connections that originate from 192.168. Whatever. And then from then on, the target is just polling accept, this accept call. And again, in the TCP transport, that's actually a call to the syscall accept. RDMA, it's listening for CM events, connection manager events, etc. And so when accept finds a new connection, it builds a queue pair object. Queue pairs are connections in NVMe or Fabric, and it calls back up into the generic code outside of the transport and says, "Hey, I found one." And the job of that generic code is then to assign this queue pair to a poll group so that it can start being polled for incoming data and process. And currently, there's actually multiple different algorithms we use to do that assignment. Originally, the release was, the first go-around was we just did it round robin, right? Just go through each one of them, spread them out. After that, an algorithm was added that tries to group all of the connections that originate from the same host, the same client, onto the same poll group. And that's just because it's very likely that if one connection is active for a particular host, the others are not. And so it sort of balances the traffic a little bit better. And then the most recent algorithm we've added is to go ask the transport what it thinks is the right poll group. And transports often have more information than we could hope to have about where it would be efficient to place that queue pair. What thread to place it on, which other connections need to be on that thread along with it. This was originally introduced for Fiber Channel because Fiber Channel only can do this transport-centric scheduling because it's not possible to, when a connection is originated on Fiber Channel, it's already associated with a particular hardware queue pair. It's already effectively in a group. And all of the connections on that hardware queue pair need to be polled as a unit. So there's only one right answer in Fiber Channel about which poll group. Every poll group is a hardware queue pair in Fiber Channel, and there's only one right answer. With RDMA and TCP, you can pick whichever one you want. It's fine. But then we started using this again, this concept again for RDMA because we, along with Mellanox, coded support for RDMA shared receive queue. And so there's considerations there on like how many total resources are available if you have a shared receive queue. So you want to ask the transport which of your shared receive queue, / queue pair pairs is best for me to give you, assign a new RDMA queue pair to. And then this is also going to end up being used in the TCP transport. It's not yet. But the Linux kernel has added a way, an interface in very recent Linux kernels to basically query the NAPI ID of a socket. And what that NAPI ID essentially means is that if two sockets have the same NAPI ID, it means they're probably originating or probably associated with the same hardware receive queue on the NIC. And so you probably want to put all of the connections from the same NAPI ID onto the same ePoll group so that you only have to poll one hardware queue pair to discover incoming packets for all of the connections. That's likely the right answer. Okay, so once the queue pair is assigned to a poll group, it starts getting incoming messages. It's a connection now, it's established. First message is always a connect message and administrative stuff, and then after that it can get I/O. And so I'll talk a little bit about what happens when it gets an I/O command on a poll group. And so while I go through this, the things to remember are that this I/O path has no locks. It touches only thread local data, so it's very cache friendly. And the most complex data structure we're going to use in this entire thing is an array. And so it's doing very, very, very simple things on the CPU that are very cache friendly, and so that's why it runs so fast. Okay, so the first thing that happens is we poll the poll group. And so the poll group calls into the transport poll group and says, do you have any connections that have incoming data? And, which makes an ePoll wait call, and then that triggers, tells us which set of socket file descriptors are ready to receive, and we call receive on each of them. And begin parsing the TCP streams if it's TCP, and we find commands. And when we have received a full command, we go to process it. And inside that command, so based on which connection it came in on, we can associate it to a subsystem. And inside the command will be a namespace ID if it's like a read or a write. And so now we know what subsystem and what namespace ID we want. And we use that information to do a lookup in the subsystem poll group, which, remember, has an array of I/O channels indexed by namespace ID. And so it uses that namespace ID from the command to do a lookup into this array, and now it has the I/O channel. If the backing BDEV is a NVMe device, this I/O channel is an NVMe queue pair. So just as a concrete example. So now we know what device it is, and we have our I/O channel for our thread, and so we submit it. We build a NVMe command, we stick it in the submission queue, and we ring the doorbell. And then we repeat. And that's it. There is polling, of course, at this top level, where when it pulls the transports, it also pulls all of the backing storage devices to ask if any I/O have completed, and it sort of does like the reverse process, goes backward through the stack to send completions out on the network. It's more or less the exact same thing in, kind of reverse. All right. Okay, and then right before we do the performance data, I just want to touch on the NVMe over Fabric's host architecture. We won't go into it in detail, but it's the same library as the local PCIe NVMe driver. Jim had pictures that showed this. So programming, writing software that talks to a local NVMe driver or to a remote device using any transport is actually the same code in SPDK. It's just the initial connect. You basically give it, you tell it connect with to PCIe on this bus device function, or you can say connect to this IP address using TCP, and then after that it's all identical. So our host, our client-side driver, also has a pluggable transport system, and it will also get, it also has support, well, currently it's just TCP and RDMA. We do not have a fiber channel initiator. We could do that. Most people just use the Linux kernel initiator there. And it probably will get some of these other more exotic transports, like user, this mediated device in user space, or anything you can imagine. If you want to give it an NVMe interface, you can just plug into that transport interface. And then it's considerably simpler than the target side because, of course, the client, there's lots of clients to one target, and so an individual client is not as complex or as heavy as the full target. So it doesn't have pull groups because you have so many fewer connections typically. You likely only have one queue pair per thread anyway, and so you don't need to pull large sets of connections. So you just create a queue pair for your thread, and then you pull the queue pair directly instead of having this group concept. But other than that, it's very similar. Okay, the fun stuff. All right, so I got two charts here of just high-level performance. One's for TCP and one's for RDMA. I just want to point out, this is this link at the bottom, which I know is terrible. You can't type that in. But these documents are all available on spdk.io/doc. If you just scroll down to the bottom, all of our performance reports are there, and they'll provide all of the details about how these exact charts were generated and how to reproduce them yourselves. This particular data is from SPDK's 19.10 release. SPDK does quarterly releases, kind of like Ubuntu or something, where the first number is the year and the second number is the month. So this is from October of last year. And we can see with this one workload I picked at QDEC64 4K 7030 mix. As we scale up the number of CPU cores, the IOPS, this has like a 100 gig NIC, so it's somewhere around 20 cores. It's really pushing the NIC pretty hard. And similarly, the average latency drops as you provide more CPU cores because it can keep up with the traffic. And so the only thing I really want to say about the TCP transport is that this is currently the most active area of development. The implementation I am showing here is more or less a what I'll term a naive implementation against POSIX sockets. And it's naive in the sense that it's like the way things were done prior to a period of innovation starting like with Linux kernel 4.14, where they've since added a whole bunch of very cool new operations you can do on sockets. And so the performance here is, it's challenged by syscall overhead primarily, which is eating up a lot of CPU cycles. And so in the master branch of SPDK, and there's several patches out, this performance changes quite dramatically. In particular, the kernel has introduced a functionality called message zero copy, which lets us do zero copy sends. And then there's also IOU ring, which allows us to batch a whole bunch of socket operations together into a single syscall. And so, we're looking at integer multiples of performance improvement, like 2x, 3x, 4x in some cases already, and we're not even all the way there yet. We haven't even used all of the cool stuff they've added. All right, here's RDMA. This is much more similar to what you'll see on the latest SPDK. RDMA is already high performance as of our original implementation of it. And so you can see here that it's saturating this 100 gig NIC at 4 cores. It's very effective. And the latency drops down really nicely to the minimum at 4 cores, where we're completely keeping up with the workload. And the latency is quite low. This is going through one hop through a switch, and this is microseconds, to real SSDs, flash SSDs. So it's, the average latency is 300 microseconds, from one system to another through a switch to a real SSD and back. So that looks excellent. And this is from the 1904 release, April of last year. I don't believe anything has materially changed as of this time, because it's already good. All right, and now I'll hand it back over to, we can do Q&A.
I'll take over at this point. We do have a couple of questions we want to get into. I believe the first one is going to be for Jim. And the question, I was able to install SPDK for NVMe over Fabric, and that seemed to create a memory-based namespace. Now I want to map the SSD present in the box as a namespace over the Fabric. How do I map a standard SSD present in a Linux box from NVMe over Fabric?
Yeah, that's a good question. So I think with some of the example configuration files we have when you download SPDK, by default it just does like a RAM disk backend, because we know that's always available in any system. But the way to do what the questioner is asking is to basically start the NVMe target. We have RPCs available to attach an NVMe controller. Once that's attached, you'll have a BDEV, an SPDK block device for that namespace. And then at that point, you can do RPCs to create a subsystem and attach that namespace, attach that BDEV as a namespace on the subsystem, and then add a listener. Basically, what's the TCP or RDMA port that it's going to listen for connections on. And once you have those pieces in place, then you'll be able to present that namespace over the Fabric. And if you have any more questions, on that, if you go out to spdk.io, you can get a link to our Slack channel, and there's always people there that are more than happy to answer questions.
Again, thank you for the added information. Next question for Ben. Ben, this one is, does Quick, when Quick is available, will it be supported? Are there any advantages using this new transport?
Yeah. So for those that don't know, Quick is an alternative network transport based on top of UDP, based originally on work out of Google, although now being standardized as part of HTTP 3. The HTTP3 specification is sort of divided into two parts. One is the actual HTTP framing, and the other is the underlying reliable UDP transport, which is called QUIC. At least colloquially called QUIC. This is definitely an area that is being actively looked at and investigated. I have been pushing pretty hard on looking at QUIC. There is no plan in the NVMe specification committee to do a QUIC transport yet, but that doesn't mean there won't be. QUIC is not officially fully standardized even for HTTP 3 yet. So it will be a while before this is complete enough to begin standardizing, a second protocol on top of like NVMe over fabrics. But for research purposes, we have been looking at this. It's very, very interesting. I think there's a couple of pros and a couple of cons. The main advantage is that QUIC at the protocol level supports multiple streams. And one of the main performance issues with NVMe over TCP is that the control messages are mixed in with the data. There's only one TCP socket per connection, per queue pair. And so it becomes really difficult to avoid copying because you don't know what's coming next, and they're not all nice fixed size things. And with QUIC, the data is all framed in the framing headers. There are streams, stream IDs, and so you can just separate the streams at a lower level, and then you have data in one place and the control messages in another. And so I think that's very, very valuable. The main downside with QUIC is that all traffic on QUIC is encrypted. So I mean, some people may say that's a positive, and sure, I think that is probably great. Storage data is typically already encrypted though, and so in most use cases this is just pure performance overhead, and so we've got to find a way to mitigate that.
Sorry about that. Next question, we'll go on to that one, is which processor architectures does SPDK support? Jim, would you like to take that?
Yeah, absolutely. Yeah, so SPDK support is primarily, we use DPDK for quite a bit of the underpinnings for doing attaching to PCI devices, doing huge page memory allocation, etc. And we basically support the same architectures that DPDK does, so x86, ARM, and then also Power. So most of that support comes from DPDK, but we do have some SPDK-specific parts that are maintained by different companies within the SPDK project.
Thanks, Jim. The final question we've got so far today is, are there any plans to extend SPDK support for other RISC processors?
Yeah, so there's no plans currently for adding support to other processors. Certainly, DPDK and SPDK are both open source projects, so if there's other processors outside of the ones that I mentioned, the facilities are in place to be able to support additional architectures outside of those.
Yeah, just to build on that, the way ARM and Power support was added to SPDK is for ARM and Mellanox came in and added support for it. And, it was not a huge number of patches. It was just a couple of places that they had to change and some barriers in the way they went. And IBM came in and added Power support. And so we maintain that, and all of the tool chain in SPDK lets you, we have cross-compiling support built in and everything. So any processor could be supported, but somebody is going to have to add the support and then be available to fix it if something breaks.
Yep.
Great. Thanks, gentlemen. Real quick, while we take a few minutes just to wrap this up, I'd like to give a big thank you to Jim Harrison, Ben Walker. Guys, presentation, excellent job today. As for everybody who is listening, please remember we'd like you to rate the webcast and provide us with any feedback that might help us in the future. As well, the PDF of the slides is available in the links section right now. They will be up on the SNEA website as well as a Q&A with all the questions and answers that were from the Q&A section. If you're on Twitter, please follow us on Twitter at SNEA NSF, I'm sorry. And last thing to cover right here, that we do have additional resources. Feel free to join us for others in the future, as well as look back at some of our archived webinars where you may be able to learn additional information. Thanks. That brings us to the top of the hour. We'll go ahead and free you guys up at this point. Thanks for joining us again. And final thanks to Jim and Ben. Thanks, guys.
Thank you.
Yep, thanks.